Hello everyone, my name is Lucas, and today I will present a joint work with colleagues from UFRJ Brazil and IRIA France. Our research is about community detection. The goal is to give a brief introduction to community detection in the first half of the slides, and in the second half I will highlight our contributions. These primarily concern how to select good candidate solutions for community detection using our concept of robustness, and also establishing theoretical guarantees that our considered algorithm can indeed converge to such candidate solution. Clustering is a well-known technique for grouping similar data points. As we can see on the left panel, it is widely used in real-world problems, from disease outbreak detection to urban planning. However, as the right panel shows, defining similarity is complex. Unlike supervised learning, there is often no single ground truth label. Different definitions of similarity or different algorithms can lead to multiple valid yet distinct clusterings. The same utility and complexity apply to community detection, which is essentially clustering in networks. The goal here is to partition the vertices of a graph into disjoint groups or communities based on how they are connected. These partitions can range from one extreme, the grand coalition where all nodes form a single community, to the other extreme, the singleton partition, where each node is its own community. To conceptualize the vast space of possible partitions, we can think of a metagraph. In this metagraph, each vertex itself represents an entire partition of our original network. For instance, the green node here represents the grand coalition, and the pink node the singleton partition. An edge exists between two such vertices if we can transform one partition into the other by changing the community assignment of just a single node. So, the distance between any 2 points in this metagraph signifies the number of individual node moves required to get from one specific partition to another. As we can see, even for a simple graph, there is a rich landscape of partitions to explore between the grand coalition and the singleton partition. Community detection algorithms typically use a quality function to score each possible partition, allowing for comparison. This scoring imposes a direction on the metagraph. Edges now flow from low quality to high quality partitions. Sync vertices in this directed metagraph are partitions where no single node move can further improve the quality score. These represent local maximum of the quality function, and many algorithms aim to find these optimal or near optimal states. One of the earliest mathematical formulations that draws a parallel to community detection is the Ising model from statistical mechanics. Originally used to describe ferromagnetism, it features a lattice of sites, each with a spin that can be in one of two states, like up or down. The Hamiltonian measures the system's total energy, which depends on how neighboring spins interact. In a ferromagnetic system, spins prefer to align. The lowest energy state, or ground state, has all spins in the same state, analogous to the grand coalition with all nodes being in one community, either all up or all down. Other configurations represent higher energy excited states. Conversely, in an antiferromagnetic system, neighbors prefer opposite spin states. In an antiferromagnetic Ising model on a triangle, frustration can arise. If spin A is up and spin B is down, spin C cannot be unaligned with both A and B simultaneously. This inability to satisfy all local interaction preference leads to frustration. A consequence can be multiple configurations sharing the same minimal energy, leading to several local maxima. The Ising model's limitation to only two states means some solutions, like placing each node in its own distinctive community, similar to a singleton partition, aren't directly representable. So, frustration in the Ising model often depends on the network topology. A square lattice might avoid it in an antiferromagnetic setup by alternating spins. However, adding diagonals, as shown in the example, can reintroduce frustration. While the Ising model provides a foundation, the Potts model offers a more direct parallel to modern community detection. It extends Ising by allowing nodes, or spins, to take on one of up to v distinct states, which we interpret as communities, and v being the number of vertices. A comprehensive objective function, or Hamiltonian, for community detection using the Potts model considers four types of pairwise relationships: internal links, internal non-links, external links, and external non-links. Intuitively, a good community detection algorithm aims to reward connections within communities, internal links, and the absence of connections between different communities, external non-links. Conversely, it penalizes the absence of connections within communities, internal known links, and connections that spans across communities, external links. If we assume symmetric weights for links and non-links, we can simplify the Hamiltonian to focus primarily on interactions within communities, effectively ignoring external interactions for simplification. This general Potts framework is powerful because many well-known community detection methods can be derived as specific instances. Starting with the simplified Hamiltonian that only considers internal interactions, a common approach to defining the internal no-link penalty, B, using a new model probability, P, scaled by a resolution parameter, gamma. The internal link reward, A, then becomes the edge weight minus this penalty. By choosing specific forms for these rewards and penalties, different models emerge. Even if these models weren't explicitly derived from the Potts model initially, they can often be mapped back to it. A classic example is modularity. In this case, we consider unweighted graphs, set the resolution to 1, and use a specific new model, the product of the degrees of nodes I and j divided by twice the number of edges in the graph. Some of these Potts variations, particularly those relying on global new models like modularity, can suffer from what's known as the resolution limit problem. The resolution parameter, gamma, acts like a zoom knob. With a low resolution, zoom out, methods tend to merge smaller, dense structures into larger communities. With a high resolution, zoom in, they can separate these cliques into smaller, more fine-grained communities. The issue with resolution limit methods is that they can behave inconsistently. For example, modularity might merge two cliques when analyzing the full graph, but then split them if we isolate just those two cliques and their connecting edges into a subgraph. This happens because the optimization depends on the global size and structure of the graph. In contrast, resolution limit-free methods, like the constant Potts model, which we'll discuss next, behave consistently. Their decision to merge or split depends only on the local structure around the communities in question and the chosen resolution value. The decision remains the same whether looking at the full network or a subgraph. These make resolution limit-free methods particularly useful when we care about local patterns and want results that are robust to change in scale. The constant Potts model, or CPM, directly addresses the resolution limit. Instead of relying on a global null model, CPM compares the presence of an edge directly against a constant resolution parameter, gamma, as seen in its Hamiltonian. This makes CPM a resolution limit-free method. An internal link contributes 1 minus gamma to the sum, while an internal non-link contributes minus gamma. This implies that gamma typically range from 0 to 1. If gamma equals 0, there is no penalty for internal non-links, favoring the grand coalition. If gamma equals 1, there is no explicit reward for internal links, but a strong penalty for internal links, favoring the singleton partition. This allows gamma to generally control the scale of communities detected. Lower gamma values favor large, potentially sparse communities, while higher gamma values favor smaller, dense communities. The resolution can be interpreted as an edge density threshold for splitting communities. However, choosing the right gamma is not trivial, as it depends on the specific objectives of the analysis. Leverage the interpretability of the constant Potts model. We further investigate the role of the resolution parameter by framing it within a hedonic game of coalitions. We retain the CPM acronym, but suggest competitive Potts model to reflect our findings. The key idea is to analyze CPM from the perspective of nodes as agents playing a coalitional game. These agents aim to increase their individual utility by forming or joining communities. While cooperation happens at the agent level to form communities, competition emerges at the community level as they dispute which node belongs to them. We show that this individual utility is aligned with a global quality function, which we call a potential that we seek to maximize. The local maximum of this potential corresponds to Nash equilibria, where no agent can improve its utility by unitarily changing communities. This framework highlights an interpersonal conflict for each node, driven by two competing preferences. When gamma is closer to 0, a node prefers communities with more friends or internal links. When gamma is close to 1, a node prefers communities with fewer strangers or internal non-links. Our main contributions are introducing the concept of robustness for equilibrium selection and providing a pseudo-polynomial proof of convergence to an equilibrium. In our work, we extend the concept of frustration to the node's perspective within this competitive Potts model. Each node effectively forms two independent rankings over potential communities. The social preference focuses as if gamma equals 0 ranks communities based on the number of friends it would have within the considered community. The antisocial preference focuses as if gamma equals 1 ranks communities by the number of strangers it would avoid. Frustration occurs for a node if its top-ranked community for maximizing friends is different from its top-ranked community for minimizing strangers. In the left example, node D is not frustrated. Its current blue community is best for both maximizing friends and minimizing strangers. In the right example, node D is frustrated. Staying in the blue community maximizing its friends, but moving to the pink community would minimize its strangers, as it cannot satisfy both preferences simultaneously. To determine a node's preference when frustrated, we derive the indifference threshold, denoted as gamma star, for each pair of candidate communities A and B that a node I might consider. We calculate gamma star by taking the difference in friends between the two communities and dividing it by the sum of that friend difference and their stranger difference. A node's move decision then depends on the global resolution parameter gamma relative to its personal gamma star for that specific potential move. For the interesting case where gamma is between 0 and 1, if the global gamma is less than gamma star, the node prioritizes gaining friends. If the global gamma is greater than gamma star, the node prioritizes avoiding strangers. If gamma is equal to gamma star, the node is indifferent between the two communities for that specific move. We can pre-compute these gamma star values for all nodes and potential moves to understand how the network structure might change as we vary the overall resolution gamma. Here we see two metagraphs for the simple 4-node graph. The left metagraph shows flows when gamma equals 0, and the right is for gamma equals 1. Notice that when gamma equals 0 on the left, the grand coalition is a sync node, meaning it's an equilibrium where no nodes want to leave. But when gamma equals 1 on the right, nodes prefer to isolate themselves rather than stay in a community with even one stranger, leading to the singleton partition being an equilibrium. The question is, at what value of gamma does the equilibrium of the grand coalition break? We can determine this by finding the individual gamma star threshold for each agent to potentially leave the grand coalition. The equilibrium breaks when gamma exceeds the minimum of these individual thresholds for any node to make an improving move. In this example, if node D's threshold to split is gamma star equals 0.33, and other nodes have higher thresholds, for example 0.67 or 1, then the grand coalition holds an equilibrium for any gamma less or equal than 0.33. Once gamma is greater than 0.33, node D would prefer to move, breaking the initial equilibrium. We define an ideal community for a node as one that simultaneously maximizes its friends and minimizes its strangers compared to all other available communities. If such an ideal community exists for a node is robust if it currently resides in its ideal community. It has no incentive to move to any other available community, regardless of gamma, because it's already in the best possible place by both criteria. A node is insatiable if its ideal community exists elsewhere, but it's not currently in it. It has a clear best move. If no single community satisfies both maximizing friends and minimizing strangers optimally for a node among the available options, a node is frustrated. It faces a trade-off, and its preferred community will depend on gamma. The definition of available communities is important here. We can allow or restrict isolation if nodes can freely form new communities, including isolating themselves. Alternatively, we can consider a fixed set of K communities. If, for example, K equals 1, where only the grand coalition exists, all nodes are trivially robust as there is no other option. We can then lift this concept of robustness from individual nodes to the entire partition by measuring the fraction of nodes within that partition that are robust. A partition is fully robust if every node within it is robust. Such a partition is stable and remains in equilibrium across the entire range of the resolution parameter, from gamma equals 0 to gamma equals 1. The robustness score can serve as a criterion to select among different candidate partitions that might, for example, all be local optima found by an algorithm. Interestingly, if we fix the number of communities k, a network can have multiple fully robust partitions at different levels of granularity, as shown in the examples for k equals 2, k equals 3, and k equals 4 using the same underlying graph. To test if our concept of partition robustness correlates with correct or meaningful partitions, we need networks where the ground truth community structure is known. Since real-world networks with unambiguous ground truth are scarce, we use synthetic networks generated by the symmetric assortative planted partition model, a special case of the stochastic block model. In this model, symmetric means that all communities have an equal number of nodes. Assortative means the probability of a link within a community is higher than or equal to the probability of a link between communities. The key parameters are the number of communities k, nodes per community n, the internal link probability p, and a difficult factor lambda, which defines the external link probability as q equals to p times lambda. A lambda closer to 0 means very distinct communities, so it's easy to detect, while lambda equals to 1 means p equals to q, making communities structurally indistinguishable from the background based purely on these probabilities. This slide shows the robustness of the non-ground truth partitions from our SAPPM generator. The top row shows histograms of this ground truth robustness, and the bottom row displays heat maps for varying internal edge probability P and the difficulty factor lambda across different numbers of communities, from k equals 2 to k equals 6. Darker purple in the heat maps indicate a higher robustness, meaning that a larger fraction of nodes in the ground truth partition are robust according to our definition. Key observations are that, generally, ground truth robustness tends to be high, especially when communities are well separated, low lambda, high P. Many ground truth partitions are indeed fully robust, meaning all their nodes satisfy our robustness criteria. Robustness tends to decrease as the number of communities increases. With more communities, there are more alternative communities for a node to consider, increasing the chance it might become frustrated. Robustness also decreases as the difficulty factor lambda increases. Communities become more similar. Or as P decreases, communities become sparser internally. This suggests that our robustness metric often aligns well with the planted ground truth structure, especially in clear community structures. So how do we find these equilibrium partitions in the competitive POTS model? Starting from any initial partition in our directed meta graph, an algorithm can simply follow any path of improving moves. That is, any sequence of single node moves that increase the overall partition quality or potential function. Eventually, such a path will reach a sync node, which is an equilibrium partition where no single node move can further improve the potential. The key theoretical question is about the efficiency. How many moves or steps might it take to reach such a sync node or local maximum? We analyzed a simple beta response algorithm like the one shown. It iteratively allows nodes to move to their currently most preferred community if that move increases their individual potential. The key to understanding its convergence lies in the properties of the global partition potential function. First, this potential is bounded. It can't go lower than approximately minus v squared or higher than v squared, where v is the number of nodes. Crucially, when a node I moves and its individual potential increases, the global partition potential increases by the exact same amount. So, local improvements directly translate to global improvements. If the resolution parameter gamma is a rational number, say b divided by c, then any move that improves a node's potential will increase the partition potential by at least 1 divided by c. Since the total possible increase in potential is bounded by 2v squared, and each step makes at least a tiny fixed positive progress of 1 divided by c, the algorithm must converge. This leads to a convergence time of O of cv squared steps, which is pseudo-polynomial because the runtime depends on the value of c from the gamma equals b divided by c, not just by the size of the graph input. The algorithm stops when a full pass over all nodes results in no nodes changing its community, as no one can further improve their potential. The Leiden algorithm, a state-of-the-art community detection method, was proposed by one of the authors of the constant spots model. It's known for its practical efficiency and quality, and it can optimize any quality function, with the CPM being its default. It consists of 3 phases. Its first phase is essentially a more sophisticated version of the beta response dynamic we just discussed. Instead of simply iterating through all nodes repeatedly, it uses a dynamic queue to manage nodes that might benefit from moving. It pops a node from the queue and discards it if there's no beneficial move to make. However, when a node moves to its preferred community, its neighbors that are not in the new community are added to the queue. This is because their optimal community might have changed due to the move. This efficiently focuses computation where it's most likely to yield improvements. Once the queue gets empty, this might not be sufficient to reach an equilibrium because moves can trigger further beneficial moves from other nodes that were not considered. Therefore, to reach a local maximum, we need to repeat this queuing and moving process. It continues until a full pass occurs where the queue empties with no nodes having moved. This ensures a stable game equilibrium is reached for this phase. The full-fledged Leiden algorithm comprises three main phases. Phase 1, local moves. This is the better response improvement phase we've been discussing. However, in the Leiden full-fledged, it typically proceeds to phase 2 once the queue gets empty. Phase 2, refinement. This is a key innovation of Leiden. After the initial moves, this phase specifically works to ensure that the formed communities are internally well connected. It might split parts of communities that are only loosely held together or reassign nodes to enhance overall cohesion. Phase 3, aggregation. The communities identified and refined are then aggregated into single metanodes. A new coercer graph is built from these metanodes and the connections between them. The entire process, starting from phase 1, is then repeated on this aggregated graph. This hierarchical approach, introduced by the Louvain method, allows Leiden to explore and review community structures at different scales. While our convergence proof applies specifically to the first local move phase, the full algorithm is highly effective and widely used in practice. Now that we have a model to generate networks with non-ground truth partitions, we can use it as a benchmark to evaluate community detection algorithm like the state-of-the-art Leiden, which optimize the CPM. We will assess performance across three key dimensions. Accuracy. How well does the partition found by the algorithm match the non-ground truth? We use the rand index for this. Robustness. What is the fraction of robust nodes in the partition found by the algorithm according to our definition of simultaneously maximizing friends and minimizing strangers? And efficiency. How long does the algorithm take to convert to a solution? We measure this in seconds. This slide presents results from benchmarking different methods, including full Leiden and just its first phase, which directly optimizes CPM, against spectral clustering for reference. The plots show 2D density contours. We are focusing on scenarios where no initial partition is available. The top row shows accuracy, rand index, versus robustness, and the bottom row shows accuracy versus efficiency. We can notice that both Leiden variants tend to produce solutions that are both highly accurate and highly robust. There is a strong concentration of solutions in the top right of the plots, indicating that robust solutions are often the accurate ones. Leiden phase 1 is particularly efficient, with most solutions found very quickly while maintaining high accuracy. Full-fledged Leiden can take longer due to its additional phases, but also achieves higher accuracy. Spectral clustering generally shows moderate robustness, and its accuracy can vary. It doesn't directly optimize for our specific robustness metric. Runtimes can vary significantly, and it's often slower than Leiden phase 1. Overall, the Leiden methods, which optimize the CPM, demonstrate a good trade-off, frequently achieving high accuracy and high robustness efficiently, especially the Leiden phase 1. This suggests a strong positive correlation between the robustness metric we defined and the actual quality of the partitions found. From our contributions and experimental findings, we can draw a couple of main conclusions. Firstly, the concept node and partition robustness, where nodes simultaneously maximize their friends and minimize their strangers within their community, can be a useful criterion for selecting among candidate community structures. Partitions with higher robustness often correlate well with the ground truth. Secondly, we've shown that a simple beta response algorithm for the competitive POTS model is guaranteed to converge to a local maximum, or Nash equilibrium, in pseudo-polynomial time. This provides a theoretical underpinning for efficiently finding this potentially robust solution. That is all I have for this presentation. I'd like to thank everyone for your attention, and I'm now open to any questions you may have.